Hello, everybody. Welcome back to Real Analysis. The last time that we met, we were proving some of the rules of differentiation: quotient rule, power rule, product rule, so forth. We have one more rule that we really need to prove. That's the chain rule. If f of x and g of x are differentiable, then the derivative of f composed with g of x is f prime of g of x times g prime of x. And we'll prove that right now. I have an ulterior motive for bringing this point out. F of x and g of x are differentiable by hypothesis. Somewhere in our proof, we're going to use the fact that they're also continuous. Okay. We have to do this case just to make sure that we don't embarrass ourselves and divide by 0. So we'll consider the case that in the immediate vicinity of x of naught, epsilon to the left and epsilon to the right of x of naught, throughout that whole interval, g of x is a constant. If that's the case, then the derivative of g is 0 because g is a constant. If we take a constant, in this case, g of x of naught, or actually, no, I don't need to do that, just g of x. For all x in this interval, g of x is a constant. So I take a constant, g of x, and plug it into f. What happens when you evaluate a function at a constant? You get a constant. So f evaluated at g of x is constant. So the derivative of f of g of x of naught evaluated at x of naught is 0. So the derivative of f of g of x evaluated at x of naught is 0. And that's going to equal f prime of g of x of naught, or f prime of g of x, no, f prime of g of x of naught times g prime of x of naught. Now this, I don't know what that is. This is the derivative of f evaluated at some constant. It's going to be a constant. I don't know what it is, but I do know what this is. It's 0. We have some constant times 0. So that's going to give us 0. So let's sum this up. The derivative of f of g of x evaluated at x of 0 is f prime of g of x of naught times g prime of x of naught. So we proved our assertion when g of x is a constant in the immediate vicinity of x of naught. I'll give you a couple seconds to look that over. For ease of notation, we'll give f of g of x a name. We'll call it h of x. So the derivative of f of g of x evaluated at x of naught is the same as the derivative of h of x evaluated at x of naught. And by definition, that's the limit as x approaches x naught of h of x minus h of x of naught over x minus x of naught. Okay, now I can go back to f and g. This is equal to the limit as x approaches x naught. Hey.
Okay. Just check it up, because I'm about to set the alarm. I won't set it since you're here.
Okay.
You got a code?
Yeah.
Okay, just set it when you leave.
Okay.
I've been working up on the roof. Hey, you got rubber shoes.
Okay.
All righty.
I'll do that. Thanks,
Have
Tommy.
a good evening.
Sure.
Yeah, the house kid told me you was up here.
Okay,
All righty.
thanks, Tom. So we're going to go back to f and g. So we have h of x, which is f of g of x, and h of x naught, which is f of g of x of naught, all over x minus x of naught, and what little trick am I going to pull here now? I think I will do this. Limit is x goes to x of naught, f of g of x minus f of g of x of naught over g of x minus g of x of naught times g of x minus g of x of naught, all over x minus x of naught. So essentially, I just divided by g of x minus g of x naught and multiplied by g of x minus g of x naught. And I can do that because g of x is not a constant, so these two things are not the same. Okay. And maybe I'll make this a little bit stronger. And just say for x not equal to x naught, for x in x naught minus epsilon, x naught plus epsilon, g of x not equal to g of x naught. So if g isn't constant, we ought to be able to do that. Here I have the limit of a product. I'm going to turn that into the product of the limits. And here's where continuity comes in. As x approaches x naught, g of x approaches g of x naught. More specifically, the limit of g of x as x approaches x of naught is equal to g of x of naught by continuity. So what we have is limit as g of x goes to g of x naught of f of g of x minus f of g of x naught all over g of x minus g of x naught times limit as x goes to x naught of g of x minus g of x naught over x minus x naught. And what is this thing? This is the derivative of f with respect to g of x. So this is f prime of g of x naught times this thing, which is g prime of x naught. So there's our chain rule. Now we'll give some consideration to relative maximums and relative minimums. let's see, do I want that to be strictly, nah, doesn't have to be strict inequality. Okay. Oh, heck. We'll go with X naught again. Okay, definition of relative maximum and relative minimum. And forgive me, I'm going to have to replenish my supplies of black markers. So if f of x attains a relative maximum or a relative minimum, and f of x is differentiable, then the derivative of f of x is 0 at that point. So here's a picture of what we're looking at. And let's say that this is epsilon, or x naught minus epsilon here. So here's our relative maximum. And here's the point x, f of x. I'm sorry, I need to write larger, forgive me. So for values of x to the left of x of naught, this is what the point x, f of x looks like. And notice that since x is to the left of x of naught, x minus x naught is negative. And notice that f of x is less than f of x of naught. So f of x minus f of x naught is negative also. So the quotient is positive. Now we'll do the same thing for x values to the immediate right of x of naught. I'm sorry, I'm not writing large enough. And we'll draw a picture of this also. Here's x, somewhere between x of naught and x of naught plus epsilon. And here's the point x, f of x. Here's the point x of naught, f of x of naught, our relative maximum. And notice what happens here. Since x is greater than x naught, x minus x naught is positive. But since f of x is less than f of x naught, f of x minus f of x naught is negative. So we have negative over positive, that's negative. Okay. This thing is less than 0. So if I do the limit, and let's see, x is to the right of x naught. So if I do the limit, x approaches x naught from the right, then this is the scenario that we're talking about. And let's see, 0 is greater than this thing. Okay. Oh, I didn't give myself enough room. This thing is less than or equal to 0, so its limit is going to be less than or equal to 0. and this is equal to f prime of x naught. And f prime of x naught is equal to the limit as x approaches x0 from the left of f of x minus f of x naught over x minus x naught. And I've sort of erased the evidence. I will put it back up here. Here's x naught, f of x naught. And let's say here's x naught. Here's x to the left of x naught. And remember how this went. X is less than x naught, so x minus x naught is negative. And f of x is less than f of x naught. So f of x minus f of x naught is negative. In other words, the top is negative, the bottom is negative. So the whole thing is positive. And notice here, x is to the left of x naught. So when x is to the left of x naught, or when x approaches x naught from the left, this thing is greater than 0. So the limit of this thing will be greater than or equal to 0. So what do we have? 0 greater than or equal to f prime of x naught greater than or equal to 0. F prime of x naught is equal to 0. So if we have a relative maximum or a relative minimum and the function's differentiable, the derivative has to be 0 at that point. Now I'm going to make a comment on this to sort of expand the consequences just a little bit. Anybody seen my eraser? No, maybe this will do it. Now, what is the contrapositive of this? So again, suppose f of x attains a relative max at x naught f of x naught. And f prime of x naught is not 0. Well, that's not exactly the contrapositive, is it? Let me do this exactly right. This is our q, we'll negate that. So we have the negation of this should imply the negation of f of x is differentiable and f of x is a relative max or min. So let's see, we negated this, f prime of x is not 0. Now, how do we negate f of x is differentiable and x naught f naught, x naught f of x naught is a relative max or min? Well, let's see, since the way to negate this is to make sure that both of these aren't true. And guess what? Our hypothesis assumes that this is true. So the way to negate that f of x is differentiable and x of naught f of x naught is a relative max is to make sure this isn't true. So I guess that explains why the derivative wasn't zero. It wasn't zero because it didn't exist. So if we have a relative maximum, either the derivative is zero or the derivative is undefined. Okay, everybody, short lecture for today. Next time, Rolle's theorem and the mean value theorem. Continue to take good care of yourselves. Exercise sound judgment. And I've told this to my other classes, I'll tell it to you too. And for those of you that are in some of my other classes, just bear with me. Don't worry about what we can't do right now. This is only temporary. Don't worry about what we can't do. Sooner or later, this will be over. And hopefully we will avoid any serious health issues. But in the meantime, just do what we can do. Don't worry about what we can't do. And I cite an example from history. Isaac Newton. He was definitely the Einstein of his century. He invented calculus. He discovered and formulated the laws of universal gravitation, things having to do with orbital velocity. His contributions to math and science were huge, and he truly was the Einstein of his century. But most people don't realize that he was in a situation similar to ours. While he was at the university in London, the bubonic plague ravaged England, and in particular London. And so to escape the plague, Isaac Newton retreated back to the family farm away from London and stayed there for a couple of years until the bubonic plague subsided. And it was during this period of time that the vast majority of accomplishments were made. The vast majority of Isaac Newton's contributions to math and science took place while he was in seclusion at the family farm, staying away from London because the bubonic plague was ravaging England. So just because we can't go to class doesn't mean that we can't do a lot. We can do quite a bit. And maybe the key is to exercise soundness of mind and take good care of ourselves. And also, don't worry about what we can't do. Let's just worry about what we can do and work on that. Clearly, that's what Isaac Newton did. And he reaped the benefits. So until next time, and I think that will either be tomorrow or the day after, be healthy and be safe.